Hello, Mr. Claudia here, and welcome to your first lesson. We're going to be starting with Chapter 1, or Unit 1, which is Exponential and Logarithmic Functions. Now, before we get to these new ideas in this chapter, we're going to do about 5 lessons review of everything related to functions. So this is all the stuff you would have done in grade 10, and especially in the second half of grade 10 in the MCR 3U course. So a lot of this hopefully is review. This lesson will also give you an idea of exactly what is expected of you from the IB exam perspective. You'll see that some of the notation and some of the things that you learned last year are a little different in the IB program. So let's go through this and hopefully it'll be a review. First of all, we want to just define the difference between a relation and a function. A relation is any set of ordered pairs. So for example, I could survey everyone in the class, ask you how much sleep you got last night and what your mark was last year, and I could plot all those points. Some relations are functions. Now, what makes a relation a function? Well, every x value is associated with only one y value. So my previous example would just be a relation because there could be a lot of people who had 8 hours of sleep last night, so it would not be a function. A few ways to think about a function. One is it's like a black box. You put something into the box and it changes it. So for example, if my function is x squared, if I put in that x equals 3, the box does something and it spits out a 9. Another thing with functions, another way to think about it, is in order to know if something is a function, it has to pass the vertical line test. That is, if I take a vertical line, so my pen, and I pass it all through all the parts of the function, if the pen ever only intersects the function once, then it is indeed a function. If it intersects twice, for example over here with this circle, then you see that that is not a function. It is just a relation. Relations are still great math things. We just can't do all the function work and all the function family things that we're going to look at. They don't apply here. They don't apply to relations. And another thing you would have learned last year is how to use function notation. So instead of saying y equals something, we write f at x, f with bracket at x. This is called function notation. And what we say, and I'll write that in quotations, is f of x. Now, if I wanted to know, well, what happens at this function when x is equal to -1? In other words, with the black box, if I put in x equals -1, what does it spit out? Well, to do that, I would sub in, so I change the x to -1, I put that in my bracket, and then I have, okay, 2 times the x, which is -1 minus 3 over, okay, -1 plus 1. And then I can solve this. Be careful with the order of operations. You have to do the top first. So -2 minus 3 and -1 plus 1 is 0. Ooh. So that gives me -5 over 0. Huh. Now hopefully you're looking at this and whoa, some alarm bells are going off. We can never have a divide by 0 situation ever in math. And that's something I did want to talk about right on the first day. We would write DNE, or does not exist. This is the one thing that can never happen. If you type it into your calculator, it'll give you an error. You can't divide by 0. Now, we don't have to go into this too much, but if you were to graph this function, then there would be some sort of hole or asymptote at x equals -1. But we'll get to that later. Essentially, you can sub in numbers and you should never get a divide by 0. Okay, now we're going to look at all the different types of functions you looked at last year. And I like to call this the function family. When my teacher taught this to me, each member of the function family had a name. So the first function that we taught you in grade 9 was the linear function. We said y equals x, but we're going to write in function notation, which is f at x equals x. Now I know what you're thinking, well, what about y equals mx plus b? What happened to that? That's okay. We're going to show that all the functions have kind of a base, kind of a parent function, and then we can make changes to the parent function. So this is the base parent linear function. And you guys know how to graph this. Probably in your sleep, it just looks like a straight line like that. The next graph we taught you, or the next function we taught you, was f at x is equal to x squared. That's the quadratic function. My math teacher called this the mother parabola. Remember, she had all different names for each member of the function family. You spent a whole course on this. Okay, so we spent all of grade 9 working on linear functions. We spent all of grade 10 working on quadratic functions. Now we kind of have showed you how functions work, and now we can introduce all these different functions in the function family to you. So cubic would be f at x is equal to x cubed, and that is that kind of neat shape with the inflection point. That's what we call that there. We would have learned sinusoidal functions. So, for example, f at x is equal to sine x. Trig functions would be another way you call this. Oops. F at x is equal to cos x. And you know, like a sine function, a sine wave, you can hopefully remember how you draw it with that kind of very recognizable repeating shape. It's not the best sine wave. Okay, then we have the square root function. So this is f at x is equal to square root of x, and that shape is kind of a rotation of the quadratic function. It looks like that. You remember the restriction for the square root function. It doesn't have any negative values. You can't take the square root of a negative. Where's my red pen here? My teacher called this square root, Sally, the square root function. Okay, we have the rational function. Now this one's a little tricky. My teacher would call it Tricky Ricky. Ricky rational function. This is f at x equals 1 over x. And you probably remember this shape. It's a really odd shape. We call it a hyperbola shape. First of all, it has an asymptote, so it has a vertical and a horizontal line, and it never touches. We'll talk more about that this week. And it has this very odd shape, right? Like that, and like that. We learned last year f at x equals absolute value of x. My teacher called this anti-absolute value function. And it looked kind of like a quadratic, but it was square like that, or that's how I think of it. And then we have a few more at the bottom there. We have an exponential function. That's f at x is equal to a to the power of x. That looks like a function. It has an asymptote along the bottom here. And oops, my pen. It goes like that. We're all really familiar with exponential graphs now. They grow much, much faster than a quadratic graph. We all know this well because of our COVID tracking graphs that we've looked at. But remember, as you go into the negative x, this approaches the asymptote but never touches it. Finally, we're going to learn f at x is equal to log base ax. This is the absolute new one that you haven't seen yet. Oh, very exciting, the logarithm. Do you want me to give you a preview of what it looks like? Well, it is just a reflection, or the inverse, of the exponential graph. So it looks like this. It starts from here, it's an asymptote, never touches, and then it explodes in that direction. So don't worry, we haven't learned that yet. But I wanted to have a page where we can see all of the different functions you're going to see in the IB program, and there they all are. Now, linear you know, quadratic you know, cubic is sort of just like quadratic. Square root is kind of this interesting half function. Absolute value. So good news, this is not in IB. So you worked on it last year. There was stuff you did last year with the absolute value function. You will not do that in this course. So that's something you can kind of forget about. And that's sort of the nice thing about IB. It does a lot of content, but it doesn't go in depth as much as the regular grade 12 program. Okay, rational functions, that's what we're doing in our next lesson, I believe, or this week. So we're going to do a whole review of those, so don't worry about that one. Sinusoidal function, trig functions. You did some of this last year. We're going to revisit this in grade 12. So you can put that on the back burner for now. We're not even going to look at it in this course. Exponential functions, that's in this chapter. And logarithms obviously are in this chapter. So when you look at all the functions, it's not actually that bad. Most of them you know, some of them you don't have to worry about, and then we're going to be reviewing some, and then some we're going to do later. So this is basically where we're going this chapter. And I like that this kind of summarizes all of our different types of functions. Let's turn the page. One great thing about functions is that once we learn how to manipulate one function in the function family, we can manipulate all the functions. They all kind of behave the same way. And one of the things you're going to see, what we've seen in your math courses so far, is related to transformations. Transformations means stretching, compressing, or moving the function, how that changes the equation and how that changes the graph. Again, you've seen this before several times, so I'm going to try to go through as quickly as possible. This should be a review. The first type of transformation is a translation. Another word you might use is a shift, or when the function has been moved. For example, let's start with a function we all know, y equals x. This is a linear function. Okay, if I add a value to the function, so if I take my function and add k or subtract k, that is a vertical translation. I either move up k or down k units. So we will get out my red pen and we will move this up 2 units. So this line, the equation is the function x plus 2. Similarly, if I were to subtract 2, y equals x minus 2. This is why we didn't teach you y equals mx plus b anymore. Y equals mx plus b is just applying transformations to the linear function. The other type of translation, or shift, or move, is left or right, a horizontal translation. And the thing about everything we do vertically tends to be more logical, so I find plus means up, minus means down. In the horizontal world, everything's backwards. So for example, let me start with what do we call this? Mother parabola, so y equals x squared. Now, if I take my function, so here, note the function notation, f at x, well, instead of f at x, it's going to be f at x plus k. That's going to be a translation to the left. So I add a value inside the bracket. Instead of going positive, it actually goes reverse. It goes to the left. So this is going to be y equals x plus 2 squared. And similarly, if you subtract a value, you're actually moving to the right by that amount. So I always think of this as reversed. Horizontal, everything is reversed. Now note the different types of transformations here. Note how you can tell whether something's vertical or horizontal. My grade 10 students always get confused. Here I'm taking the function and I'm adding a number to it, or subtracting a number. So my function is y equals x, so I'm taking that function x and I'm adding 2 or subtracting 2. That's how I get these equations. Over here, I'm taking the function and I'm subbing in, I'm replacing the x and subbing in x plus k. Just like over here on our first page, I replaced all these x's with -1. Here I'm replacing all these x's, the x here, with x plus k. So I take out the x and I put x plus 2, and that's in brackets. All of that is squared. That's how we get a horizontal translation. We're doing the thing inside the bracket, I would say, in quotations. Whereas over here, I'm doing it outside the bracket. Again, you guys have done all this. You can teach it all to me. You don't even need me to explain it, probably. But I'll just write here in a little note, this is telling you to sub x minus k into x. I try to put everything on the paper here for you to study. I try to be as complete as possible. So I'm going to put one little note up here. Sometimes IB writes translations as a, b. This is just goofy IB notation, but you might see it. This is the horizontal translation, and this is the vertical translation. Just something to be aware of. Okay, let's keep going with our transformations. So now we're going to look at reflections. So let's start with a function. How about anti-absolute value? So there we go, like this. Oh, very poorly drawn. Hopefully you do a much nicer job. Y equals absolute value of x. Now, if I take this whole function and I put a negative in front of it, it's a reflection in the x-axis. Well, this is my x-axis here, so you imagine there's a mirror there, so it's reflected in the mirror, and I see the reflection down here. So I think of it as an up-down reflection. You can call it whatever you like. Well, you have to know the notation. Reflection in the x-axis. Okay, then we'll look at the other type of reflection. Again, this is if I sub in negative x. So for example, if I draw this function, hopefully you remember that this is the exponential growth function. So y equals 2 to the power of x, for example. There's our asymptote. So if I were to sub in negative x here, I'd have 2 to the negative x. That's an exponential decay graph we'll look at later, but it should be a reflection around the y-axis. So it's like my mirror is here. So this half gets reflected over here, and this half gets reflected over here. So it looks like that. And it's y equals 2 to the negative x. I've replaced the x with negative x. Okay, and just to note, I mean, this absolute value function, if I were to reflect it in the y-axis, it would look the same, right? It wouldn't have changed much. So there's a reason I chose this one for this example and this one for this example. Okay, the final type of transformations are stretches. So stretch and compressions, I should say. Two sides of the same coin. Let's start with a function, the cubic function. Hopefully you remember how to draw that. It's got that nice little inflection there. Y equals x to the 3. Okay, so now if I take that function and I put a number in front, a constant in front, that's going to stretch the function vertically by whatever that number is. So if I choose the number 2, if I put a 2 in front of this function, it's like I got this vice grip and I pulled the function this way. And you can imagine if you pull it, you're going to stretch it like silly putty, and it's going to become a lot like kind of thinner and more stretched out like that. So that would be y equals 2 times x to the power of 3. That's hard to see. That's all great. But if you see this little note here, if I put a number between 0 and 1, that's what this means, right? P is greater than 0, P is less than 1. So in other words, P is between 0 and 1. Then this function, f of x, is compressed by a factor of P. So if I choose a number, say 0.5, then I'm going to compress the function by half. So I'm going to take my function and I'm going to squeeze it, compress it. Okay, finally, if we're doing a horizontal stretch. So this time we'll start with everyone's favorite, which is a sine graph. So it's got like this kind of sinusoidal graph. You want to leave some space. So this is y equals sine x. Okay, this is, like I said, like before, this is reversed. This is how I think of it, at least. So here, if I put a large number in front of the function, it gives me a vertical stretch. In this case, if I put a large number in the function, it gives me a compression. So in other words, if I put a large number like 2, so if I sub in 2, so q is 2, then I'm going to replace this x with 2x, so I get sine 2x. That's a larger number, so I'm actually not making it, not stretching it like you'd think I would. I'm compressing it. I'm squeezing it by 1 over q, or I'm squeezing it by 1 over 2 in this case, making it half as wide. So my sinusoidal function is going to look like this. So even though it's a big number, it's actually doing the opposite. It's squeezing it when I look at things horizontally. Squeezing it by a factor of 1 over this number 2, so half. The reverse is true. If q is a big number, then it's horizontally compressed by a factor of 1 over q, or it's, in other words, it's stretched. So for example, if I put in the number half, in this case, q is half, then I have f at half x, so I replace the x with half x. It's a small number, it's a fraction half. You'd think it would be compressing, but it's doing the opposite. I'm doubling the graph, so it's going to become very, very wide. Y equals sine half x. So this is reversed. That's the important thing to know. I think we can get really confused in semantics here. It's important for you to just know what you have to do. For me, it's a big number means stretch here, small number means compress, big number means compress here, small number means stretch. It's the opposite. Those are all my different transformations, and those transformations apply to any function that we looked at in the function family. And the amazing thing is I can apply multiple transformations to get the more complicated graphs. Let's do that in an example. So turn the page. For example, sketch the graph of x squared, and on the same set of axes, sketch the following graphs. Now this is a real IB question, and you'll notice there's no craziness here. They often like to see you build the function one step at a time. So let's put that as a note. This is a big IB hint. This is a big IB requirement. Perform multiple transformations. Step by step. And I will just put as a little note to help you, usually do the stretches and compressions first. If you want to minimize your headaches. So let's do this question. So f at x. Okay, well, it said sketch the graph. So let me sketch that graph. So this is y equals x squared. Great. Okay, for part A, I need to put a negative. I put a negative in front of the whole function. Remember what I tried to explain? If you have something in front of the whole function, you're probably doing it vertically. If I go back, the negative in front means a vertical reflection or reflection in the x-axis. So that means I'm going to take this whole function, I'm going to mirror it in the downward like this. So this is y equals negative f at x. Okay, my next step, part B, I have to, take what I had, so negative f at x, but now I'm going to sub in 2 here. So if I look at this, I should be able to say this is this was a reflection in x-axis. I should look at this and remember, okay, well, I'm subbing in a number, so this is a horizontal stretch or compression. Well, remember for horizontal it's reversed. If I put in a big number, it's actually compressing. So this is a horizontal compression by in half, 1 over that number. So I'm going to take what I have now, my red one, right, the negative f at x, and I'm going to compress it in half. So it's going to be something like that. Great. And my last step is to add 3. And notice I'm adding 3 to the whole function, so this is a vertical translation up. Vertical shift or translation up 3. So I take this whole function and I move it up 3, so it's going to be somewhere here. And that is y equals negative f at 2x plus 3. Notice how we did one thing at a time. That's a real life IB question. So there you go. You would have gotten great on your IB exam. Finally, the last thing about functions that we need to talk about is domain and range. And this is probably the first thing you would have done with functions. That's why we're doing it today. Domain we know is all the x values in the relation, and range is all the y values in the relation. If you're ever forgetting, my hint is call the doctor. You can remember, hey, call the doctor. You'll remember, well, x always comes first, y always comes second. Or maybe you'll just remember that domain always means x, range always means y. Now, be careful here. There's a few differences from what you would have done last year. So let me show you. Let's start with a graph that looks like this. So this is negative 4. Okay, so domain is all the x values. Now let's start by just talking about in words. Well, the x values for this function are all the x values from negative 4 and continuing forever. But there are no x values less than minus 4. So in words, which you'll never be asked to do, but I just like to do it to make sure we're all clear. The words I would say from negative 4 to positive infinity. You guys know that notation, right? This is infinity. The range would be all the y values. Well, the y values, okay, this is y equals 0, so there's no y values above 0. So it'd be from 0 to negative infinity. Let's do words for all of these, then we'll look at the different types of notations. The next graph I'm going to draw looks like this. Forgive me, that's not already drawn here. There's an asymptote at y equals 0. Again, we'll talk more about asymptote, but that is the line that the function approaches but never crosses. And there's also a hole, and that hole is at x equals 3, y equals 2. You would have done a lot of this last year, looking at continuity.
Could Joanne Mayer please call extension 6012? Joanne Mayer, please call extension 6012.
Okay, so let's talk about this. So this is a what is this? An exponential function with a hole or some sort of. Okay, so let's talk about this function here. Let's talk about the x values. Well, it looks like you would have all the x values continuing forever to negative infinity, and all the x values continuing forever, right? Because this line will keep going forever. However, there is no x value at x equals 3. There's a hole there. The function is missing. So if I want to talk about the domain in words, I would say it's all the x values from negative infinity to positive infinity, except x equals 3. What about the range? Well, the range is all of the y values. Here we see that we have all the y values going up to positive y, positive infinity. Then we have all the way down to almost y equals 0. There's nothing below that. But at y equals 0, well, the function is never actually going to reach y equals 0. This is an asymptote. So if I continue forever in this direction, this line is going to get very, very, very close to the asymptote, but it will never touch. So again, we're just writing in words for now, but I would say from just above 0 to positive infinity, all of those y values except y equals 2. There's a hole there, so there's no value at that point. Okay, and let's look at one more function before we start looking at notation, and this is going to be a piecewise function, when you kind of a weird one. So we'll start down here. This is 2. This is a -3. So it's a piecewise function like that. Let's see how well you remember stuff like this from last year. So I've tried to map out all the different points you'll need for this one. So piecewise function has 2 different pieces. This is a weird function. Well, wait, is it even a function? Does it pass the vertical line test? Well, if I run a pen through this function, it always intersects the function only once. So yes, it is still a function. We still have to consider it a real function. The domain, well, that means all the x values. So I have all the x values from -3 all the way to 2. But note the circle there, that means that it's a hole, or it's not including the point on the axis. So it would be from negative -3 to just before 0 and just after 2 to 4. Okay, the other x values are from just greater than 2 all the way to 4. So note the difference, right? The colored in dot means I include that value 4. The circled dot there means that I do not include the value 2. Similarly, the range is from -3, so the y values are from -3 to just before -1, and from the range goes from -3 all the way to just before 2. I mean, if you look at it, I include -3. I don't, all of these y values up to -1, but then -1 does exist over here, and includes all these y values until just before +2. Okay, so that's how I talk about domain and range in words, but we need to show you how to write this in math words. No one's ever going to accept if you write out words like that. So the one way we write the domain and range is using set builder notation. And this is the one I prefer, where you use kind of braces to show that you're talking about a set. Here in this case, it's a set of x values such that x is greater than or equal to -4. So let's just digest this a little bit. This is telling me, the brace here is saying the set of x. The line here means such that. So I'm saying, hey, you want to know the domain? Well, it is all the set of x's, so all x's, such that x is greater than or equal to -4. So x can be greater than -4. So -3, -2, -1.556, +10, +1,000,000. All of those x's are valid domain. And that's exactly what we wrote here in words. For range, I need to write y's that are, between 0 and -infinity, so smaller than 0. So for my range, it's going to be y such that y is less than or equal to 0. Notice that because I'm including the point that is on y equals 0, I have to write the less than and equal to 0. Okay, another type of notation is called interval notation. This is a different way of writing things. This is where I just write the two kind of endpoints. So in this case, I have -4 and +infinity. The only thing about interval notation is you have to be very careful about the brackets you put around it. If you put a square bracket, it means that you're including the value. So -4 is part of the set. If I put a round bracket, it means that you're not including the final value. So this is from -4, including -4, all the way up to, but not including infinity, because you can't count to actually get to infinity. So it's all the numbers up to, but not including. So I'm going to just write a note there. Square means included. Round means not included. For range, we're looking at all the y values from -infinity all the way to 0. I include the 0, I don't include the -infinity. Those are the two types of notation. You can choose whichever you like, but you have to be comfortable looking at both, because IB might send you either one on an exam. Okay, let's just do these last few questions. Okay, domain here for set builder notation. Okay, so it's domain, so I'm dealing with x such that, and we said all the x values except for x equals 3. I know in previous courses our teachers might have said you have to write x belongs to the reals, but that is a kind of extra notation that isn't as explicitly stated in IB. So all we have to say is x such that x is not 3. We know all the other x's are part of it. For the range, well, we know we're dealing with the y's such that, okay, well, the y's have to be greater than 0. Right? It was all greater than 0. It does not include 0, so I don't put the equal to 0 because that's not part of it. We also know that y cannot equal 2, so I put a comma and put that restriction as well. For interval notation, well, there's a few intervals here. For the domain, there's an interval from -infinity all the way up to x equals 3, and then from x equals 3 all the way to positive infinity. So there's this set, -infinity to 3, union 3 to positive infinity. We call this the union. It's telling you you have to consider both of these sets. The first set is from -infinity to 3. The round bracket, though, tells me not including 3. So everything up to and including 3. This second set is from 3, but not including 3, so just greater than 3, all the way to positive infinity. That's why I find this is a lot easier. I find this can get a little awkward. Similarly for range, the range is all the values from 0 to 2, but not including 0, not including 2, union 2 and positive infinity. Whew. Okay, finally, for this piecewise function, the domain is x such that, okay, well, I have all the x values from -3 to just before 0. So from -3 to 0. Notice that I have the equal to -3 because that's included, but I have just less than 0 because I'm not including this point on 0. And you can get used to writing things in this notation. This is my left bound, this is my right bound, this kind of x between two things. But that's not all. There's also all the x's between 2 and 4. 2 and 4. However, 2 is not included, but 4 is, so I write it like that. The range is all the y values such that, okay, so this is from -3 y to 2. But we know that this point at -3 is included, and the 2 is not included. Again, this is confusing because it jumps, but it still includes all of these values. All the y values in between are part of my range. For interval notation, I have to show these two sets. So I have -3, 0, union 2, comma 4. I just have to decide on my brackets. The -3 is included, so it's a square. The 0 is not, so it's round. The 2 is not, so it's round. The 4 is included, so it's square. For my range, I go from -3 all the way to 2. 2 is not included, but the -3 is. Just make my one note here. I already talked about this. You would write x belongs to the real set of numbers, y belongs to the real set of numbers if no restrictions. But I don't require you to write that out every time, just if there are no other restrictions. Phew, and that's our first lesson. I mean, that's the entire functions course right there. So hopefully it was mostly review. There's just a few things to get used to. Just because it's IB doesn't mean it's harder, and in a lot of cases what you did last year might have been harder than what you're going to see on an IB exam. Nevertheless, please take a look at the homework and make sure that you're comfortable with these things. It's also a good review. It looks like a lot, but a lot of these questions are very short, or some of them just require some quick sketches. So take a good, try those out, and we'll take a look at them. Thanks everyone, and we'll see you next time.